Newton's second law dictates that the sum of all forces divided by the mass of the object being acted upon times the time interval that the forces act in is equal to the change in velocity. Put in a more usable form, this relationship is given by the final velocity is equal to the initial velocity plus the effect of all forces. This means that no change in velocity occurs without a force, for both stationary objects and moving objects. We can test Newton's second law by observing an object in the real world that seemed to have no net force acting on it. If it turns out that that object has no change in velocity, as we can verify by using VIDLE, a modeling program, then Newton's second law will be verified. To track this particular object, a tube of chapstick, its position was marked frame by frame, and because the object's motion was not exactly perpendicular to the camera, the axis was tilted slightly to best capture the horizontal motion. Once we have this data, we can use the first 2 points to find the object's initial velocity using the formula change in position over change in time. Using the calculated initial velocity and the given initial position, 0, 0, we can make a model using our fundamental principle in VIDLE. The velocity, 0.415 meters per second in the positive x direction, is hard-coded in, as is the initial position. We set the time to 8 seconds because that is the duration of our recorded footage, and the ball's velocity and position is defined recursively and respectively by the effect of the forces, which in our case is all 0, and the effect of the velocity, which is simply linear, multiplied by the change in time, which for this program is 1/100th of a second. Again, because there are no forces, we expect the ball to move with constant velocity. When we run the program, we see that this is the case. It moves with constant velocity in the straight line. We can export the position data from both programs and compare them in this Google spreadsheet. As we can see here, the model slightly underestimates the experimental position, but otherwise is a fairly good approximation. This is probably because the first 2 data points used to calculate initial velocity were taken while the object was still speeding up, so accepting a human error, the model was accurate. This means that an object with no net force maintained constant velocity, verifying Newton's second law. But what if the axes by which we measure our motion were flipped? Well, the coordinates of the data points would be the coordinates of the data points would change, so all of these would be negative, but their relationship to one another would not. The velocity would technically be in a different direction, but the speed would be identical. Now, we were saying that this object had a net force of 0, but is it possible for us to say how many pushes and pulls, or constituent forces, are combined to give a 0 net force? The answer is not really. We may know the net force, but we don't know all the forces that contribute to it. That's like giving someone the number 5 and asking them if it's made up of the numbers 2 and 3, or 1 and 4, or vice versa. A physicist may be able to point out particular component forces like gravity or the normal force, but judging solely by observing the object's change in velocity, we can only know for sure what the sum of the forces is, or the net force.